You may as well.
Yeah, might as well. So, everyone, welcome to the Data Geeks Saturday event. This is pretty exciting. And one of the things that I hope you learn is that we don't have to go back to the future in order to, get any real advantage of this. We're actually going to go to the past a bit and go back to some basics and talk about what the basics are of database normalization. I believe in presenting topics that are the basics that a lot of people seem to overlook. And it's the things that people trip up on when they're trying to implement because they're too excited to go after the shiny new toy and they want to get in and get things done. And then they wonder, why didn't things work the way I expected them? And so that's why we want to cover these basics. So one of the things you're probably wondering about is just who is this guy? So I am an enterprise data architect at Health First, and it's an insurance plan out of New York. And I have been involved in the PASS community for quite some time. In fact, at one time I was the local leader for Indy PASS, and I've spoken at SQL Saturday events across the country since 2012, the east to the west coast and north to south, and I've had a load of fun doing that. I did get a Bachelor of Science, Computer Science degree in, back in the 80s at Ball State University, and I got a Master of Science in Computer Information Systems. And when I got into healthcare, I was a glutton for punishment and went back for a Master of Science in Health Informatics. And I even got a certification along the way. But the point is I've been doing this for over 35 years and I love it. And I love to be able to do what I can to help. So what we're going to talk about today is what is database normalization? We need to answer that question because it comes up quite a bit, a lot more than you would realize. We're going to talk about some use cases, and we're also going to talk about goals. And when we get into the normal forms itself, we'll cover what these normal forms mean. Then the part that a lot of people get confused about is we're going to talk about denormalization, or what can you do when you do it backwards, when you denormalize data structures. We're going to look at the reasons why you would do that, some of the methods that you would use, and the potential drawbacks and gotchas that could be there. And we'll cover all that before we get to some closing thoughts. So here's something to consider. Ted Codd is considered basically the father of databases, relational databases. He said every non-key attribute must provide a fact about the key, the whole key, and nothing but the key. And I love the play on words because if you follow that to its logical conclusion, then that would mean that the key is the truth. And I couldn't agree more because the key of a record is what it uniquely identifies it. So let's talk about what database normalization is. The intent behind database normalization is to reduce data volume for inserts and updates. Why do you want to do that? First of all, it's because you want to speed things along. You want to solve for database anomalies and errors, and you want to improve data integrity. So if you think about this, that the data volume, by reducing that, makes the inserts and updates faster, and that will reduce the data anomalies and errors, which then in turn improves data integrity. So we're going to talk about a couple of use cases. Mainly it's for highly transactional systems. This is where it really came about because they wanted to be able to do things quickly and to do it in an efficient manner. You also want to consider with situations where space is a consideration because a normalized database uses less space because less data is stored. You don't replicate the data in multiple places. And you also want to consider where width of a row is an issue. For example, if you have a really wide table and you're going to bring back all that data in every row of data in your query, it's going to take longer. And so you want to be able to speed things along by making them shorter. So let's take a look at first normal form. In first normal form, the first rule is that every column in the table must be unique. And that means that you don't want to use multiple fields in a single table to store similar data. Now, for example, if I can have email 1, email 2, email 3, and I can have ID 1, ID 2, ID 3, ID 4, and I can repeat those. But there's a lot of space that's being wasted if we don't populate them. And if you do have a set limit, like say 10, what do you do when you get to the 11th? So it causes problems when you want to add additional values. The other thing is that you don't want to store multiple values in a single field. For example, I don't want to have in my email an abc@def.com, a comma, or some other separator or a space, and then another email address, because then that is not making that data unique. You want to have discrete values in your data so that you have one data element per field in a record. Rule 2 says that separate tables must be created for each set of related data. Basically, what this means is that you want to have separate tables that will handle multiple column instances. So I want to take a contact table and separate that out. So I have all the fields for that contact table. I want to take everything related to emails and put that in a separate table, phones, etc. And I can break them up into separate tables, not having it all in one table in one row. It gives you flexibility because you're able to have a variable number of values without making modifications to the table structure. That way, if I want to have, like I said, 10 email addresses and I specify 10 fields when I get to the 11th, well, what do I do? By having it in a separate table, then I can have 0, no records for that particular relationship, or I could have many. I can go beyond 10, I can go beyond 20, whatever is needed for that application. And it doesn't require any change to the data structure or the application to be able to do that. You also want to be able to group related columns together. So for example, if I want to say I've got an email address and an email type, etc., everything related to do with emails, I can put those together in that table. It allows me to maintain my logical grouping of related data so that things make sense when you look at it from a higher perspective. The third rule for first normal form is that each table must be identified by a unique primary key. Now, if you were in the session we had just previously, Deborah went into a great deal about what unique primary keys are. So I'm not going to cover that so much, but I will say that the primary key is a unique identifier that is for each row. Now, the primary key can be one field, such as in a surrogate key, or it can be multiple columns. But that primary key says this is what makes this record unique, like no other record in this table. As I mentioned, it can consist of one or more columns, and this is what is usually referred to as a natural key, where we can say I want last name and first name. Those two together are going to be my unique key. Or I can use the surrogate key where I want to have a replacement value for that. So if I have a number of fields that are complex for my natural key, I can create a surrogate key or a replacement key that is short and it's abbreviated and easy to manage. And I can use that in place of the longer key. But I still have to maintain my uniqueness in my record. So for example, when I'm creating a record in my contact table, I can call it a contact ID. The fourth rule in first normal form is that no rows may be duplicated. So in other words, you don't want to have the same record in there multiple times. Each row must be unique, and the primary key helps to enforce that uniqueness. If you need to have multiple columns of repeating data, then maybe you need to put that out into a separate table so that you can have it broken out and then have multiple rows to represent that data. Rule number 5 says no columns may be duplicated. And this goes back to what we talked about before, where I don't want to have, a contact, or say like phone number. I don't want to have another column that says phone number. If I need to have 2 different types of phone numbers, I can label them separately. So I don't want to have a duplicate column. I don't want to store the same data in another column in the same row. So we want to make sure that we don't have redundant data either in rows in our table or in columns. The 6th rule says that no row or column intersections contain a null value. And basically what this is saying is that in the original definition for forced normal form, it didn't allow for null values. However, not to get on a soapbox for that one, but null values do have their place, and there are considerations that we need to take into that. So again, like I said, some methods don't allow for null values. Like for example, a bit value. A bit value would be either 0 or 1. That shouldn't have any null values because it's a binary value. If you were to make that a nullable value, then you would end up with a trinary state. Some values you want to use default values for, such as an ending effective date. You can put that into a date out in the future, like December 31st, 9999, or something of that nature. Rule number 7 says we don't want to have row and column intersections that contain multi-valued fields. This goes back to where I was saying earlier about having multiple email addresses in the same text field. So we want to have only one value per column in a row. And if you have any questions about that one, see rule number 1. So here's an example. I have a table here that I've defined as my contact table. And I have in there, of course, my first name, last name, work phone, cell phone, email 1, and email 2. Now, in order to make this in a true first normal form, I would want to break this out and say, here is my contact table, here is my phone table, and here is my email table. And then I can separate data. So I can put my names through here. I can put the work phones, cell phones, etc. into the phone table. And then I can also separate out the email addresses into multiple records. This data set then fits first normal form. Then we get into the second normal form. And its first rule says that we have to create separate records for sets of values that apply to multiple records. What this means is that we don't want to have values that are used in multiple tables that really should be in separate tables. For example, if we say I have a phone type and email type, I separate those out so that I can identify what my types are. We also want to ensure that we have values that are consistent no matter what their various uses are. We also want to maintain data that's identified by the primary key that is specific to that key. You don't want to represent data from in one record that really belongs in another record. Rule 2 says that we want to associate related tables by a foreign key. And again, Deborah went through this in the previous session. So the foreign key is think of it as a stored reference to another table's primary key. It's a link between the two tables, the record in that table. So for example, in my contact ID, that's my primary key for my contact table. And my phone table references that as a foreign key because it says this record is associated to this particular contact ID record. It ensures that we have only in one table that we have corresponding rows for the other one, because you want to make sure that they're all associated appropriately. You don't want to have a foreign key that represents an incorrect value. Also, with foreign keys, they don't have to be unique, like we would consider for primary keys, because multiple rows, for example, multiple phones numbers or multiple email addresses can be referencing the same contact ID. So you want to keep that in mind. It doesn't have to be unique in that table. And it is also allowable that a foreign key can be null if it's not applicable. So for example, if I have a record that I'm storing in my contact table, and then I have a foreign key to something else and it's not applicable, then that value can be null. So in my second normal form structure that we had earlier, this is my first normal form. To break it in the second normal form, I would take the contact table and the phone table and email, but you notice I put in what my phone types are. Instead of using a word to specify what my type was, I use I create I said that wrong. I'm creating a key for the contact ID, which is my foreign key back. So, sorry, back here. This creates that foreign key back to this table because instead, right as before, this was by itself. It didn't have any reference to the contact table. So we put those contact IDs in there. And third normal form is where we eliminate fields that don't depend on the primary key, things that are restricted by what that unique primary key is. And so values that are part of the record, but they don't define what that record's key means or what the meaning of that record is, we don't want to keep in the table. We don't want to store data that's better suited in another table as well. For example, on phone type and email type values, we want to define them in their own tables. Now, this is where you get into some situations where, well, maybe we want to consider performance because now we're breaking out into yet another level of tables. So when we get into talking about denormalization, then we'll talk about striking a balance for performance. So for example, we take our second normal form tables that we had here, and what I've done is now I take the phone contact is the same, but you notice that in my phone, I've broken out the types. Instead of using a word for that, I've broken that out into an identifier so that it has its own phone type table. And I would do the same thing for the email. So that email is broken out into its own table, and I just didn't have enough room to display it here. And believe it or not, there are other normalization forms. Most people only go to about the third normal form, and that's usually what's effective. But there are some others, and I'll just briefly touch on them. For example, there's the Boyce-Codd normal form. It's sometimes called like a 3.5 because it's not quite, it's past beyond a 3, but it's not quite a 4. And that just basically says where you don't have any more than one candidate key for a table. Fourth normal form says that we don't want to have a data or that a table shouldn't contain 2 or more independent and multi-valued data. And in most cases, if you're meeting third normal form, you shouldn't really reach the fourth. That shouldn't be an issue. Fifth normal form says that you can't break it out into any smaller tables. And so that's kind of one of those quasi ones where, you know, most people say, well, if I meet third normal form, then I'm basically good enough. And sixth normal form, it's been proposed, but it's not even well defined, so I'm not even going to mention it. And if you're interested in the others, you can look those up. So let's take an overview of what database normalization is. Our goals, remember, are to reduce our data redundancy. We want to eliminate how much data that we're storing. We want to get rid of anything that is duplicative so that we don't store it twice. Because if you store things twice and then one gets changed and not the other, then you're questioning what's really true. And if you have discrepancies like that, that causes your data to become more suspect. If you're not having a single source of truth, then you'll have errors in your data and such discrepancies like that. And also, all of this is to improve your data integrity. And if your data integrity is improved, then your performance will improve as well. Again, there are exceptions. I have seen systems that were, how shall I say, hyper normalized, where it went a bit too far in creating too many tables with small values that could hinder performance, because then we're dealing with a lot of tables, especially when I want to do a report query and I'm having to do, a dozen joins in order to get a simple set of data. So that can hinder performance. So keep that in mind. Excuse me while I take a drink. Okay. I want to take a pause here and see if there are any questions. I don't know that if I have a moderator in my session, but I am looking at the text sessions.
I have not seen any hands or any questions at this moment.
Oh, okay, thank you. I appreciate you being here. So we will continue. I love this quote that the Dalai Lama said, that to know the rules well so you can break them effectively. And by understanding what the rules of data normalization are, allows us to be able to break them effectively and to be able to make them work for us instead of having to work against us. And then when we're talking about database normalization, I always like to think of, I missed something here. I like to think of this. I'm an old fan of the movie, and I love the reference to Abby Normal. So Young Frankenstein is one of my favorite movies. So denormalization is not just like Abby Normal. It is allows us to optimize data for reads. Now, keep in mind that denormalization does mean that we are creating more copies of the data. We are violating the rules of data normalization for a purpose. When, especially like in data warehouses or operational data stores, if you have too many tables, it can make your queries too complex. It can make the execution time and performance to be really burdensome. It can increase your IOs because of the number of joins. So by keeping duplicates in your data, you're able to reduce those queries or reduce the number of tables in your queries so that they can perform better. Now, remember, normalization is still important, especially if you're doing this in a transactional system or in an environment that you have to make sure that your data integrity is of the highest, and you want the performance and the speed for data inserts and updates. But if you're doing this for a reporting system, then it's okay to denormalize that to a bit. But there are still some rules that you should follow, and keep in mind the circumstances that you have. For example, if you want to maintain history in your data, if you want to see what the historical changes to data are over time, there's a couple of methods that you can use. One of them is that you can have multiple time-based records in the same table, where you can have, say, an effective and expiration date sets for each record. And then when you query the record, you can say which one is effective at this date or in this time period. And then you would select the correct record. Or if you want to say what were the last 3 to 5 record changes, or what changes were made in this record in the last 6 months, then you can get that from that table. Basically, what you're doing is that you're replicating the rows, your primary key changes, because your primary key is going to occur in multiple rows. So you have to add an additional value, which would be your effective and expiration dates to that, so that you can maintain your data integrity, or use a surrogate key for that. The second one is to be able to have a separate historical data table. So let's say I want to capture a change log. And so in this log, for every table, every row, every column that changes, I'm going to write a record in this table for every one of those. Now, it may not be the most efficient for terms of, I want to see what's the given state of this record 6 months ago and see the whole record. That one is a little more difficult to pull. But that one is more useful if you're wanting to look at a particular value in a record and say, this one was changed. Who changed this and why? And when was that changed? Then you can look at your data log for that. But the idea is to be able to reproduce data as of a given date and see what those changes were and to capture them. Of course, SQL Server has implemented a lot of features, such as the time features in certain tables that you can activate, and that makes it a lot easier. But if you're not using SQL Server, then you can use one of these two methods. Another reason to denormalize data is to enhance query performance. Like I mentioned earlier, if you want to reduce the number of joins that's used in a query, especially for reporting, I know a lot of systems you have to generate reports quickly, or you want to generate it for dashboards or for inquiries that need to be have a quick response. So you want to reduce the number of joins that you have to be able to get that data. It's also useful to take data that rarely changes, say a lookup value. So if I have a code and a description and I want to capture that as it was at that time and store it in my denormalized record, then that way I don't have to look up that code value each and every time. I have it there at that point. The added benefit is if that code value changes or the description for that code changes, then you've captured what it was as it was at that time when the record was written. You can also combine used queries into a fixed result set. So if I say, I went to, I have this query I use a lot and I run it an awful lot, I can take that and fix it into a given data set and I can update it each time. In certain databases, they call them materialized views, like in Oracle and Postgres, and SQL Server, they're called index views. So you can use that as an example of a denormalized data set. A third option is that if you want to accelerate your reporting, you want to make it easier to use, you can pre-aggregate data that is often used for reports. Let's say that you have a daily report and you want to capture at each hour, but a given set of that data is the same for the whole day. You can aggregate it once and then just show the changes over time. An example of that are for totals and averages and statistics and all that fun stuff. You can calculate it once, and let's say, especially if the data doesn't change much during the day or you're doing just hourly reporting, you can capture it and then present it as it's needed. You can reduce impact on your source systems as well because you're not pulling that data in so much each and every time. And it also allows you to give more people the same data with lower costs. It also helps you to simplify database management. For example, if I can pre-calculate these values, then I'm avoiding those on-the-fly calculations. I'm saving time, I'm saving resources, and I can make sure that my reports are more consistent so that what displays in 1 minute will display also the same in the next. It also helps me to avoid logic from being implemented in more than one place. So I don't have to have code or logic code in this report and this report and this report when they're basically similar or they use similar structures. I can calculate it once and have them query off of that. I can even go so far as to say, well, I want to simplify my ETL and I will use this aggregated data for that. Another thing is if I want to store derived data. So a lot of times derived values are frequently needed, but they don't change that much over time. So when those calculations are made, I can capture that and then just reuse them each and every time, unless that the calculation changes. So if they're not updated that often, I can store it once and reuse it multiple times. I can also take pre-joined tables and store those results. So if I have My order header and my order detail, I'm always querying those together. Maybe I can make a composite of the order header detail and store that, and then just reference that when I want to. Especially if I don't care about how quickly I need, or I mean how recent the data needs to be, I can pull that more quickly. I can also take the lookup and reference values and store those in the record. Then I don't have to reference those at all in my queries. I don't have to go and say, well, here is my phone type, and go and see what that the code for that is and get its value, because then I can look at these up once, store them, and there I go for reporting purposes. I can also keep details in a master record. So let's say, for example, my order header, if I have, say, an aggregate of my order details, I can store that, pre-calculate it, and put it in my master record so I can have a quick reference to that without having to calculate it each and every time. I can also do the reverse. Let's say that I'm going to be storing a detail record or referencing detail records in a report, but there's information in the header that I want. I can bring that down into another data set and then capture that at the detail level and see what my header is for information for that. And so it eliminates the need to read one table or the other, depending on which one that you're avoiding. Now, unfortunately, there are drawbacks. Every process that you go through to denormalize data does have a cost to it. For example, one of them is the obvious. It requires additional storage space. There are additional columns that you need for deduplicated data. It takes additional rows, especially for the historical, or even when you're capturing data to lower grains. The method of capturing historical data can make a difference on how much space that you need. And most often, these are stored on separate servers even to minimize the impact. So you don't put this data, historical data on your source system, you pull it over into a reporting system, a data warehouse, or an operational data store. Also, you want to have additional documentation, because now you're not only replicating the data, but you're also replicating the logic that's used. You're replicating what data can be used under what circumstances. So you're going to increase your need for documentation. And as with any other system, if you don't have good documentation, then it's going to mean that the system will not be used properly. And so you want to have that. You want to also have good ETL requirements, because now you're replicating that data in multiple places. You want to make sure that the data that's in place A is the same as the data that's in place B. So that way you don't have discrepancies in that data. And if you have those discrepancies, then you're opening yourself to potential data anomalies. Because if that data is out of sync, then you're going to get a report that shows one value and a report that shows another, and they're supposed to match. And if they don't, then you've got issues with that. So your data anomalies can increase with that, which is one of the whole reasons why we're doing data normalization to begin with. It also means that you're going to have additional logic, so that you're going to have to perform a similar ETL operation in multiple places. So you're going to have even potentially the same code replicated elsewhere. How you calculate your aggregates is going to have to be duplicated in multiple places. And it can make your transformations even more complex. Now, keep in mind that data denormalization is intended for reporting purposes. So if you're doing inserts and updates into a system that is denormalized, it will slow your inserts and updates. It will make them more complicated. It will cause them to take more time, take up more space. And your data is only going to be as current as the last update that you had in your modified tables, or in your denormalized tables. So let's take a look at a few common denormalization scenarios. For example, let's say name parts. I say I've got a last name, first name, middle name, suffix, prefix, and these are multiple names. Now, if I were to do this in true normalization fashion, then I would create a separate table that has each of the name parts and a code and a field that says here's what that name is. And in order to get the full name of a person, say their prefix and their say, you know, like it's Dr. Dr. Jones, Dr. Indiana Jones. So you're going to get those three parts. You're going to have to read three different records and then put it together to get that full name. Does it meet normalization rules? It sure does. But is it practical? Probably not. And so that's why in most scenarios, we denormalize that into a single record and we create them as separate fields. Address is another example where we usually denormalize it. For example, you have address line 1, address line 2. Some may have address line 3 and 4, and then you have your city, state, and zip, and there are other fields as well. So by true normalization rules, we would take the address lines and put those in a separate table. But that's really too normalized for most purposes, so we will denormalize that and capture it as a single record. Now, if you're, you know, some places like Amazon will actually capture those in separate tables so that you can have multiple fields. But typically only one or two are needed, and they're not often normalized for that. And like I said, address lines are often kept at 2. I've seen 3 maybe at a max, and they fix those field names as address line 1, 2, and 3. Any questions so far about what we've covered?
At this moment, I don't see any hands. I don't see any comments.
Okay. All right. Well, let's talk about what we've covered then. So we talked about database normalization and its use cases and goals. And again, the idea is to be able to limit the amount of data that's being stored so that we have a single source of truth and that we store the data as few times as possible so that we can speed things along. We can make inserts and updates happen more quickly. We want the records to be short. We want them to be so that there are only a few fields so we can improve I/O. We also talk about the normal forms and what that represents for us and all the rules for that. And then we also talked about the denormalization and the reasons that we would denormalize so that we can improve read performance. We can spread data out. We can pre-calculate data so that we don't have to calculate it on the fly all the time. We can also have multiple copies of data so that we don't have to read multiple tables. We can also have multiple methods so that if I want to have a copy of data over here for these types of reports and a copy of the data over here for these types of reports so that they're not colliding with each other and causing so they're not causing resource problems. Again, like I said, most tables should at least be second normal form. I've seen database applications that work very well in second normal form. Many of them went to third normal form, and sometimes it was too much so when it's appropriate, use third normal form, but it's not always practical. There's an application I work with now that took that idea of normalization to a degree where we have to read several tables deep in order to create a record. And it was designed for the application, and so I'm sure the application works speedy quick on that, but for any use outside of that, it's difficult. So we take that data and we put it into another database where it's broken out and denormalized for reporting purposes. Especially if you have a database that's heavily normalized. I mentioned about impeding performance. So you do want to strike a balance. If your primary purpose of the database is for an application, then normalize as much as possible. And if it's for reporting purposes, then you want to denormalize so it makes it more effective. So design with normalization in mind first. That way you start with what really needs to be broken out appropriately and to limit your data duplication. And then denormalize it so that it makes sense. You can't get away without performing proper analysis on your data, and that includes performance, what your use case are. It isn't just about how the data is structured and how it's organized, but also how it's going to be used. You want to focus on the parts that really need the help. It's likely that you may want to denormalize only certain aspects of it to help with performance. But do some studies, do some tests on it, and fine-tune your queries. I found that in some cases, people will say, well, I need to denormalize it because the queries just don't perform right. And then you actually look at the queries and find out, oh, well, it's because you're referencing the same table twice, or you're doing the query incorrectly and it's causing more of a performance problem. So fine-tune your queries first, and if it still doesn't work, then look at denormalization. I like to look at it again where I normalize first and then denormalize only where it's necessary. But really, experience is going to be your guide, both trials and errors. That's going to guide you on how you're going to build your system, how you're going to modify it, how you're going to tweak it. I like the expression to normalize until it hurts, denormalize until it works. That means you're going to go as far into normalization as you can until it becomes a problem. And then back it out, denormalize it to a point where it truly works. And I think that regardless of what your application is, whether it's a high-speed online transaction processing system, or if it's going to be a reporting system, if you take that approach for each and every system, then you'll strike the right balance that you need for your data and for your application. I do include some references in here on a normalization and also on denormalization that may be useful. So when you get a copy of the slides, take a look at the links here and learn more about what normalization and denormalization does for us. Also, when you receive the slides, there are links here for free ebooks from Microsoft, Redgate, and SentryOne, which are totally awesome. They are really helpful. Some of them are a bit dated, but there are also newer books in there as well. And I would appreciate feedback on the presentation, on its content, how I did as a presenter, so that see if I can do better the next time when I not only want to give this presentation, but any other. These feedback on these presentations not only make the presenter better, but almost makes the overall event much better. And here is my contact info. If there are any questions, I can be found at SQLRV.com. I'm on Twitter, LinkedIn, and you can email me at aaron@sqlrv.com. And again, I open the floor to any questions.